You have been told your entire life that Earth is small. What nobody tells you is that when you compare Earth to the true scale of the universe, the word small completely breaks down. There may not even be a human word for how insignificant we really are. If that idea sparks your curiosity, subscribe now, because this story is about to shatter everything you thought you knew about our place in the cosmos. Get ready. Let's begin. Stand in a field in rural America on a clear night. No city lights, no noise, just darkness and the Milky Way stretching overhead, a dense river of stars so thick it looks almost solid. And in that moment, without thinking, you feel it? You are at the center of all this. Everything is arranged around you. That feeling is not stupidity. It is ancient. Humans have carried it for thousands of years, on every continent, under every sky. And for most of history, the greatest minds on Earth agreed. Then 1924 arrived, and everything broke. Before that year, the scientific consensus, not folk belief, not religious doctrine, but the formal position of the world's leading astronomers, was that the Milky Way was the entire universe, not part of it, not a significant portion of it, all of it. Everything that existed within our galaxy. The universe and the Milky Way were, by scientific definition, the same object. This was not a fringe position held by cautious thinkers afraid of new ideas. This was the accepted truth, supported by the best data available, defended by some of the most rigorous scientific minds of the 20th century. And they were wrong, not slightly wrong, not wrong about a detail, wrong in the way that changes everything, the kind of wrong that, once corrected, makes the old picture of reality feel like a childhood drawing. To understand how thoroughly wrong they were, you have to go back to 1920. That year, the National Academy of Sciences organized what historians of astronomy now call the Great Debate. It took place in Washington, and it pitted two serious, credentialed, deeply intelligent men against each other over a question that sounds almost quaint in hindsight. What are the spiral nebulae? Scattered across the sky were faint, smeared patches of light with a distinctive spiral shape. Astronomers had cataloged them for decades without reaching any agreement about their nature. Were they relatively nearby clouds of gas within the Milky Way? Or were they something else entirely? Something far larger, far more distant, and far more unsettling. Harlow Shapley took one side. He was, by any measure, a formidable scientist. He had already done something remarkable. He correctly mapped the size of the Milky Way and placed the sun far from its center, out in the galactic suburbs, 2/3 of the way toward the edge. This was a genuine and important achievement. But Shapley was also convinced that the Milky Way was everything that the spiral nebulae were small, local structures nestled within our galaxy, not independent systems in their own right. Heber Curtis took the other side. He had been studying the spiral nebulae carefully and had come to a different and deeply uncomfortable conclusion. These objects were not inside the Milky Way. They were outside it. Each one was an entire galaxy, an island universe. As the phrase went separated from us by distances that made the width of the Milky Way look modest, both men brought evidence. Both men made errors. And the outcome was, in the most precise sense, a draw. The data in 1920 was not yet decisive enough to settle the question. Shapley left Washington still convinced. Curtis left unsatisfied but undefeated. The debate adjourned without a verdict. The situation was almost perfectly ironic when you step back and look at it clearly. Two people inside a house, arguing about the dimensions of their rooms. One has correctly measured the interior. The other suspects the building is unusual in some way. Both are applying rigorous methods, deploying serious mathematics, marshaling every observation available to them. And neither one knows, because neither one can yet see out the windows, that their house is a single unit in a neighborhood that stretches in every direction as far as existence goes, containing structures just like theirs beyond any count. That is where astronomy stood in 1920. The universe, by official scientific reckoning, ended at the outer edge of the Milky Way. Beyond that, nothing. Not unexplored space, not distant objects too faint to see. Nothing. The question had not even been properly formed yet. There was no beyond to wonder about. Shapley, it should be said, did not take the subsequent years well. As new observations began accumulating, as the numbers started pointing, quietly but insistently, toward the conclusion that Curtis had been broadly right, Shapley did not revise his position quickly or gracefully. He pushed back. He looked for alternative explanations. He held on. This is worth pausing on, because it is easy to read the history of science as a clean march from error to truth, carried forward by clear-eyed rationalists who follow evidence wherever it leads. The actual history is messier and more human than that. Shapley had publicly committed to a position. He had built part of his reputation on a particular picture of the cosmos. Letting go of that picture meant admitting, in front of the entire scientific community, that he had been wrong about something fundamental. Genius does not dissolve the ego. Intelligence does not eliminate the very human reluctance to be publicly wrong about something you care about. Shapley was not a fool. He was a brilliant man who had staked a claim, and staked claims are hard to abandon. The universe, however, does not negotiate. The evidence kept arriving. The spiral nebulae kept behaving in ways that made no sense if they were small and nearby. The distances implied by their brightness, their spectra, their structure, all of it kept pointing outward, further and further, into a space that the official model said did not exist. And in California, on a mountain called Wilson, a man was already spending his nights solving the problem. Not with theory, not with debate. With a telescope, the most powerful in the world at that time, and with a kind of patient, obsessive precision that turns ambiguous data into undeniable fact. He was not a theorist working quietly at a desk, building models and arguing from first principles. He was a man who pressed his eye to a lens through long, freezing nights and looked, and measured, and looked again. 4 years of that. Thousands of observations. Hundreds of photographic plates cataloged and analyzed in the cold dark above Los Angeles. And one night, he found something in the data that no one had expected. Something that did not fit the model. Something that, once measured and confirmed and announced to the scientific world, made the entire accepted picture of the universe the one Shapley had defended. The one the greatest minds of the century had constructed and endorsed collapse overnight. Not gradually, not through years of slow revision. Overnight. One man, one number, one night. And the universe humanity had known for all of recorded history, the tidy, bounded, singular Milky Way cosmos was gone forever. But the person who changed everything was not a theorist working at a desk. He was a man who pressed his eye to a telescope through long, freezing nights in California, and he saw something no one expected to find. His name was Edwin Hubble, and in the autumn of 1923, working alone through the night at the Mount Wilson Observatory in the mountains above Pasadena, California, he found what he was looking for. The instrument he used was the Hooker telescope 100 inches of mirror, the most powerful optical telescope in the world at that time. It had been completed in 1917 and had already produced remarkable work, but nothing it had done before, and very little it would do after, would matter as much as what Hubble accomplished with it in the months between 1923 and 1924. He was studying the Andromeda Nebula, that faint, smeared patch of light that had been sitting in sky catalogs for centuries, without anyone knowing what it truly was. Shapley had looked at it and concluded it was a relatively small, relatively nearby gas cloud tucked inside the Milky Way. Others had suspected something grander, but suspicion is not measurement. Hubble was there to measure. What he needed was a specific kind of star, a Cepheid variable, and he found one. Then more. A Cepheid variable is a star that pulses. It brightens and dims in a regular clockwork cycle, some over days, some over weeks, and this rhythm is not random. In 1912, an astronomer named Henrietta Swan Leavitt had discovered something extraordinary about these stars. The longer the period of their pulse, the more intrinsically luminous they are. The cycle and the brightness are locked together by physics, reliably, everywhere in the universe. This turns a pulsing star into a cosmic measuring tool of almost absurd elegance. You observe a Cepheid. You time its pulse. From the period alone, you calculate its true luminosity, how bright it actually is, intrinsically, at the source. Then you measure how bright it appears from Earth. The difference between true brightness and apparent brightness is a function of distance. Simple mathematics from there. The star is, in effect, a lighthouse of known wattage. You see how dim it looks from where you stand, and you calculate exactly how far away it must be to appear that dim. Hubble found Cepheid variables inside the Andromeda Nebula. He timed their pulses. He ran the mathematics. And the number that came back was not the number anyone in the astronomical establishment was prepared to receive. 900,000 light years. That was his initial estimate. 900,000 light years from Earth to Andromeda. The entire Milky Way, Shapley's grand, definitive, singular universe was roughly 100,000 light years across. Andromeda, by Hubble's measurement, was 9 times further away than the full diameter of everything astronomers had been calling the cosmos. It could not be inside the Milky Way. It was not a gas cloud in our backyard. It was something else entirely, a colossal system of stars lying at a distance that simply had no precedent in any prior human conception of space. Hubble announced his findings in January of 1924. The scientific world did not slowly warm to the idea over years of gradual persuasion. The response was immediate and decisive. The evidence was too clean, the methodology too sound. Within months, the debate that had stalemated in Washington 4 years earlier was effectively over. The spiral nebulae were not part of the Milky Way. They were other galaxies. The Milky Way was not the universe. It was one galaxy among an unknown but certainly enormous number of others. And Hubble's initial number of 900,000 light years, it turned out, was itself an underestimate. Later measurements, made with more refined instruments and better calibrated stellar data, corrected the figure upward. The true distance to Andromeda is 2,537,000 light years, not 900,000. More than 2.5 times further than Hubble's already staggering original estimate. In a single announcement, the known universe expanded by a factor that has no clean analogy in human experience. The Milky Way had been everything. Now it was one, not the largest, not the oldest, not the most significant, just one. A single galaxy among others, sitting in space that turned out to be incomparably vaster than any model had accounted for. Think of it this way. You have spent your entire life in a small town. You know every street, every building, every face. You have explored every corner of it, mapped it carefully, and concluded reasonably, based on everything you have ever seen, that this town is the world. The world is exactly this large and no larger. Then one day you climb a hill at the edge of town, reach the top, and find yourself looking out over a continent, cities in every direction, stretching to every horizon, more of them than you could count in a lifetime. Your town is still there behind you. It is exactly the size it always was, but it is not the world. It is a single point on a map so large Your previous conception of scale no longer has any meaning. That is what Hubble did to humanity's map in 1924. And the revision did not stop there. Because as telescopes improved and techniques refined and decades of observation accumulated, the number of galaxies in the observable universe kept growing. Hundreds of thousands, then millions, then hundreds of millions. Then, in 2016, a team led by Christopher Consolis published an analysis in the Astrophysical Journal that synthesized deep field observations from the Hubble Space Telescope with statistical modeling of the galaxies too faint and distant to observe directly. Their conclusion: the observable universe contains at least 2 trillion galaxies. 2 trillion? Not 2 billion? 2 trillion. A 2 followed by 12 zeros. If you counted one galaxy per second without stopping, you would need more than 63,000 years to reach 2 trillion. And that figure covers only the observable universe, the portion whose light has had time to reach us in the 13.8 billion years since the Big Bang. The actual universe, by most cosmological models, extends far beyond what we can observe. The 2 trillion is a lower bound on an already incomprehensible number. And the Milky Way, in that context, is nothing special. This is perhaps the detail that lands hardest when you sit with it long enough. Our galaxy is not unusually large. It is not unusually old. It does not occupy any privileged position in the cosmic structure. By every measurable parameter, the Milky Way is a mid-sized spiral galaxy, not large, not small, not particularly luminous, not located in any especially dense or interesting region of the cosmic web. Unremarkable, in the most literal sense of the word. There is nothing about it that would make an observer from outside our galaxy point at it and say that is significant. The sky you see from that rural American field, that river of white fire, that ceiling of ancient light, is one ordinary galaxy out of 2 trillion, a single grain of sand, on a beach that goes on past the horizon in every direction. So if the Milky Way is just one average galaxy among 2 trillion, then who is our nearest neighbor? And when you find out how large they actually are, you will understand why we are the small ones in this relationship. Go outside on a clear night and find Andromeda. It is the farthest thing the human eye can see without a telescope, 2,537,000 light years away. And when you find it, your first reaction will almost certainly be disappointment. A faint smear, barely there. The kind of thing you second-guess yourself about, wondering if you are actually seeing it or just willing it into existence. Small, distant, completely unthreatening. That instinct is wrong, catastrophically, almost personally wrong. That smear of light contains approximately 1 trillion stars, not 100 billion, not 200 billion. 1 trillion. The Milky Way holds somewhere between 200 billion and 400 billion stars, according to estimates from NASA and ESA. Even at the absolute high end of that range, Andromeda still outnumbers us by a factor of 2 to 3. In raw stellar count alone, Andromeda does not compete with us. It simply outclasses us and has for as long as both galaxies have existed in anything like their current form. The physical scale confirms the same verdict. The Milky Way stretches approximately 100,000 light years from edge to edge. Andromeda stretches approximately 220,000 light years, more than twice as wide. If the Milky Way is a 12-inch vinyl record sitting on a turntable, then Andromeda is a record more than 26 inches across, sitting on the same turntable, in the same neighborhood, and outweighing us by roughly the same ratio it outmeasures us. This has never been a relationship between equals, not even close. To understand the full weight of that imbalance, you have to pull back from the two galaxies themselves and look at the larger structure they share. The Milky Way and Andromeda both belong to what astronomers call the local group a gravitationally bound collection of more than 54 galaxies spread across a region of space roughly 10 million light-years across. 54 galaxies sounds like a crowd with meaningful diversity. The mass distribution tells a different story. Research by von der Merel and colleagues mapped out exactly how mass is allocated within the local group, and the result is almost uncomfortable in its lopsidedness. Andromeda and the Milky Way together account for somewhere between 85 and 90% of the total mass of the entire local group. Every other galaxy in that collection, all 52 remaining members combined, makes up the leftover 10 to 15%. The local group is not a community of peers. It is a system built around two dominant bodies, with everything else orbiting at the margins, gravitationally subordinate, going wherever the two giants pull them. And between those two giants, Andromeda holds the stronger hand: more stars, more mass, more gravitational reach. In any honest accounting of who runs the local group, Andromeda is the answer. We are the secondary partner, the lesser anchor, the smaller record on the turntable. The situation of the smaller galaxies scattered through the local group illustrates this with a kind of quiet, cosmic humor. The Magellanic Clouds. The large and the small are visible from the southern hemisphere as two bright, detached patches of light, distinct enough to carry their own names, prominent enough that ancient navigators used them for orientation. They are often described as satellite galaxies of the Milky Way, which is accurate in the strict technical sense. But satellite is a polite word for what is really happening. The Magellanic Clouds are going where the Milky Way goes. They have no meaningful say in the matter. They are small boats tied to the stern of a much larger vessel, moving with it not by choice but by physics. The same principle extends to the dozens of dwarf galaxies distributed throughout the local group. The Sagittarius dwarf galaxy is already mid-digestion. Its stars pulled out into long tidal streams that now wrap around the Milky Way in slow loops, the remnants of a smaller structure that drifted too close and is now being unraveled thread by thread over hundreds of millions of years. These small galaxies do not have independent trajectories in any meaningful sense. They orbit, they drift, they get absorbed. The gravitational architecture of the local group was set by Andromeda and the Milky Way, and everything else lives inside that architecture without any power to reshape it. None of this makes the night sky less worth standing under. The faint smear of Andromeda is still one of the most astonishing things available to unaided human vision: an entire galaxy. 1 trillion stars, crossing 2.5 million light-years to arrive at your eye as a ghostly whisper of light. That is not diminished by knowing what it actually is. It is transformed by it. You are not looking at something small and forgettable. You are looking at the dominant mass in your cosmic neighborhood. You are looking at something that outweighs everything else you can see, everything else in your galactic corner of the universe, by a ratio that makes the word neighbor feel almost absurdly inadequate. It has been sitting there the whole time, every clear night, every generation of humans who looked up and saw that faint smear and thought nothing of it. 1 trillion stars, hiding in plain sight, wearing the disguise of insignificance so convincingly that it took humanity until the 20th century to understand what it was actually looking at. And even now, knowing the size, knowing the star count, knowing the mass, there is still a tendency to think of Andromeda as a static fact, a large thing, at a fixed distance, not going anywhere, something to measure and catalog and appreciate from afar. The way you appreciate a mountain range visible from your window. Impressive, permanent, not your problem. That tendency is the next mistake. Because Andromeda is not sitting still. It is not maintaining its distance. It is not content to remain 2,537,000 light-years away while we go about our business in the Milky Way's outer suburbs. It is moving. It has been moving for a very long time. and the direction it is moving the single fact about Andromeda that changes everything else about how you understand your position in this galaxy, in this local group, in this universe, is directly toward us. But size is not the most disturbing thing about Andromeda. What is disturbing is that it is moving and it is heading straight toward us. The size is one thing. The star count is one thing. But to understand what Andromeda actually is, not just how large, but what kind of object, what history it carries, what it has already done in the billions of years before we started paying attention, you have to go deeper than dimensions. You have to look at the interior. Start with mass, not the number of stars, which is an impressive count, but an incomplete picture, because stars are only part of what a galaxy weighs. Dark matter, gas, dust, stellar remnants, all of it contributes to the total gravitational mass of a galaxy. And that total is the number that matters when two galaxies begin pulling on each other across millions of light years. For Andromeda, that number was established in a 2010 study by Watkins and colleagues, who analyzed the motions of satellite galaxies and globular clusters orbiting Andromeda to back-calculate the total mass required to produce those orbital velocities. Their result, approximately 1.5 trillion times the mass of the Sun, 1.5 trillion solar masses. The Milky Way, by comparable estimates, comes in somewhere around 1 trillion solar masses, though the uncertainty on both figures is significant enough that some studies place them closer together, and others place Andromeda's advantage at a larger margin. What is not in dispute is the direction of the difference. Andromeda is heavier, substantially heavier. The gravitational dominance suggested by the local group mass distribution is not a statistical artifact. It is a real physical property of a real object that outweighs us by hundreds of billions of solar masses. At the center of that mass sits something proportionally formidable. Every large galaxy hosts a supermassive black hole at its core, a gravitational anchor of almost inconceivable density, formed over billions of years through the accumulation of infalling matter and the mergers of smaller black holes. The Milky Way's central black hole is called Sagittarius A star. It weighs approximately 4 million times the mass of the Sun. For years, the image of Sagittarius A star released by the Event Horizon Telescope in 2022 was the closest thing to a direct portrait of it that humanity had ever produced, a ring of superheated gas glowing around a darkness so complete that light itself cannot return from it. Andromeda's central black hole is called Messier 31 star, and it is in a different category entirely. Estimates of its mass range from 55 million to 230 million times the mass of the Sun. Take the lower bound alone, 55 million solar masses, and it is already more than 13 times heavier than the black hole at the center of our own galaxy. At the upper bound, it outweighs Sagittarius A star by a factor of nearly 60. The object sitting at Andromeda's core, drawing everything inward, anchoring 1.5 trillion solar masses of galaxy around itself, is one of the largest black holes in the local group, and it has been growing for billions of years. But the mass and the central black hole, as striking as they are not the strangest thing about Andromeda's interior. The strangest thing is what the core looks like when you examine it closely enough. In 1993, a team led by Todd Lauer used the Hubble Space Telescope to image the center of Andromeda at a resolution that had not been possible before. What they found did not match what the models predicted. Instead of a single bright nucleus at the galaxy's center, the standard configuration, the expected architecture, they found two distinct brightness peaks, sitting close together but clearly separate, designated P1 and P2, a double nucleus. Two cores where there should be one. The Hubble Space Telescope confirmed the observation. Subsequent studies refined it. The double structure is real, stable, and has persisted long enough to be a structural feature of Andromeda rather than a transient event. P2 is the true dynamical center, the location of Messier 31 star, the supermassive black hole. P1 is offset from it, brighter in certain wavelengths, an eccentric disk of older stars orbiting the black hole in an elongated loop that brings them closer to P2 on one side of the orbit and farther on the other. When they are at the near point, they cluster together and produce a second brightness peak, visible from 2.5 million light-years away. Why does this structure exist? The leading explanation is that Andromeda absorbed another galaxy at some point in its past. A smaller galaxy drifted too close, was captured by Andromeda's gravity, and was gradually torn apart and incorporated its stars, its gas, its stellar remnants pulled into the fabric of the larger system. The double nucleus is the residue of that absorption, the echo of a meal. P1 is not a separate surviving core from the consumed galaxy? The detailed dynamics argue against that straightforward interpretation, but the unusual stellar distribution it represents almost certainly traces back to a merger event that reshaped Andromeda's central architecture billions of years ago. Think of a large python that has swallowed something significant. From the outside, long after the fact, you can still see the shape of what it consumed, a distortion in the body, a remnant of the prey visible through the predator's form. Andromeda carries its history in its structure the same way. The double nucleus is not a curiosity. It is a record. It is evidence that what we are looking at is not a pristine, undisturbed galaxy sitting quietly in space. It is a system that has already acted on the universe around it, that has already reached out, captured, consumed, and integrated. That carries within its geometry the proof of what it has already done to something else. This reframes the neighbor entirely. The object that appears as a faint smear on a clear night, the thing that looks small and harmless and barely worth noticing, is a galaxy with 1.5 trillion solar masses, a central black hole between 55 and 230 million times heavier than the Sun, and a double nucleus that records a past merger written into its core structure. It is not a passive presence. It is an entity with a history of gravitational conquest, visible in its own architecture, still legible billions of years after the event. And now it is looking in our direction, not metaphorically, physically, measurably. The light from Andromeda that reaches your eye on a clear night is 2.5 million years old, but the galaxy it comes from is 2.5 million light-years closer than it was when that light departed. It has been moving toward us the entire time. It has never stopped. And the gravitational relationship between Andromeda and the Milky Way, between 1.5 trillion solar masses and 1 trillion solar masses, bound together across the local group, ensures that it will not stop. The galaxy that consumed another and kept the evidence in its core is heading toward the galaxy we live in. It has been doing so for longer than our species has existed, and the speed at which it is closing that distance is something no human technology has ever matched. And the speed at which it is approaching, you will not believe it because it is faster than anything humanity has ever built, by a factor of hundreds, and nothing, not even the expanding universe, can stop it. You have probably heard that the universe is expanding. It comes up often enough in science communication that most people carry it as background knowledge, a settled fact. Something Edwin Hubble himself first measured in the late 1920s, when he noticed that distant galaxies were receding from us in all directions. Their light stretched toward the red end of the spectrum by the very fabric of space, growing between us and them. The universe is expanding. Everything is moving away from everything else. The cosmos is getting lonelier by the billion years. The natural inference, the one almost everyone draws without thinking about it, is that Andromeda must be moving away from us too. It is out there, 2,537,000 light-years away. And if the universe is expanding uniformly, then the space between us and our nearest large neighbor must be growing, slowly but relentlessly, the way everything else in the universe is drifting apart, right-wrong, completely, entirely, consequentially wrong. Andromeda is not moving away from us. It is moving toward us, directly toward us. At approximately 68 miles per second, which is 245,000 miles per hour, or roughly 110 kilometers per second. According to measurements from ESA and the Hubble Space Telescope, that number has been confirmed repeatedly through radial velocity measurements of Andromeda's light. Through proper motion studies, tracking the galaxy's actual angular movement across the sky over years of observation. Through multiple independent methodologies that all converge on the same uncomfortable conclusion. To put that speed in terms that mean something, the Apollo 11 spacecraft, traveling from Earth to the Moon, flew at approximately 2,040 miles per hour. Andromeda is closing the distance between itself and the Milky Way at a speed more than 120 times faster than the rocket that carried human beings to the Moon for the first time. And unlike Apollo 11, which had a destination it eventually reached, and a trajectory that eventually ended, Andromeda has no destination except us. It is not slowing down in any meaningful sense. It is not going to pass a certain point and stop. The gravitational relationship between the two galaxies ensures that the approach continues. The mechanism behind this requires a moment of explanation, because the apparent contradiction is genuine and worth resolving clearly. How can the universe be expanding while Andromeda is approaching? The answer lies in the relative strength of two competing forces at different scales. Cosmic expansion, the stretching of space itself driven by dark energy, does act on everything, but its effect per unit of distance is extremely small. At the scale of megaparsecs, the distances between galaxy clusters, dark energy wins. Space expands faster than gravity can pull things back together, and galaxy clusters drift apart from each other over cosmic time. That is the expansion you hear about. That is the force making the universe lonelier. But at the scale of the local group, at the distance of 2,537,000 light-years, separating the Milky Way from Andromeda, the combined gravitational mass of both galaxies is overwhelming. 1 trillion solar masses pulling from our side. 1.5 trillion solar masses pulling from Andromeda's side. Together, more than 2.5 trillion solar masses of gravity reaching across that gap. The expansion of space is real, and it is acting on the distance between us, and it is losing. Gravity is winning, has been winning, will continue to win until the two galaxies meet. The analogy is two bullets fired toward each other into a headwind. The wind is real. It slows both bullets, but the wind is not strong enough to reverse their trajectories. They are going to meet regardless. The only question is when. NASA scientists ran the numbers with precision in 2012, using data from the Hubble Space Telescope combined with gravitational modeling of the local group's mass distribution. Their conclusion: the first close encounter between the Milky Way and Andromeda will begin approximately 3.75 to 4 billion years from now. The full merger, the process by which the two galaxies cease to be distinct objects and become a single new structure, will be complete approximately 6 billion years from now. 4 billion years. 6 billion years. Those numbers are large enough that the human brain cannot actually process them as durations. 4 billion years ago, Earth did not yet have complex life. The oldest animal fossils in the geological record are younger than that. The entire evolutionary history of multicellular life on this planet fits inside the window between now and the first Andromeda encounter, with time left over. So in terms of anything that affects anyone reading this, or anyone who will ever live on Earth in any recognizable future. The collision is irrelevant. 4 billion years is enough time to comfortably not worry about your dentist appointment next Tuesday. But the physics of what will happen is not irrelevant. It is, in fact, one of the most thoroughly studied and precisely modeled events in all of astrophysics, because the outcome is predictable, the timescale is defined, and the processes involved illuminate everything about how galaxies form, evolve, and transform over cosmic time. We know what is coming with a level of detail that is, given the subject matter, almost unsettling. And almost everything most people assume about what a galactic collision looks like is wrong. But this is the part most people get wrong. When two galaxies collide, what actually happens to the stars? The answer will completely shatter whatever you have been picturing about a cosmic collision. 1 trillion stars moving toward 200 to 400 billion stars. The numbers alone suggest something cinematic and catastrophic, a titanic smash-up. Stellar debris flying in every direction, suns destroyed by the billions. The fundamental architecture of two galaxies ground into wreckage by the sheer violence of impact. The scale of the objects involved seems to demand a proportionate scale of destruction. The reality is almost the opposite, and understanding why requires confronting just how empty a galaxy actually is. A galaxy looks dense. In photographs, especially the long exposure images from the Hubble Space Telescope or the James Webb Space Telescope, a spiral galaxy appears as a continuous sheet of light. Arms of brightness winding outward from a luminous core. Stars packed so tightly they blur together into a single glowing structure. The visual impression is of something solid, something full. That impression is a lie told by the limitations of imaging and the vast multiplicative power of luminosity. Galaxies are not dense. They are, by almost any measure that matters to physical objects, trying to occupy the same space, almost entirely empty. Consider the Sun. It is approximately 865,000 miles in diameter, large enough that 1 million Earths could fit inside it. The nearest star to the Sun is Proxima Centauri, at a distance of approximately 4.24 light-years. 1 light-year is approximately 5.9 trillion miles. So the gap between the Sun and its nearest neighbor is roughly 25 trillion miles. Now translate that into a comparison the human brain can actually hold. If the Sun were reduced to the size of a basketball and placed in the middle of New York City, Proxima Centauri, also reduced to the size of a basketball, would be sitting in Los Angeles. The nearest star, at basketball scale, is on the other side of the continent. That is the average spacing inside a galaxy. Not the spacing between galaxies, the spacing between stars within a single galaxy. The objects are enormous by human standards and separated by distances that make the word vast sound inadequate. When the Milky Way and Andromeda collide, this emptiness is the critical fact. 1 trillion stars moving through 200 to 400 billion stars sounds like impact. What it actually is, geometrically, is two enormous collections of objects separated by such vast average distances that the two populations pass through each other the way two swarms of gnats flying in opposite directions pass through each other in the dark. They interpenetrate. They occupy the same volume, and almost nothing touches. NASA and ESA simulations of the Milky Way-Andromeda merger have calculated the probability that any two individual stars will actually collide during the entire process. The number is so small, it barely registers as a meaningful probability. The universe of stars involved numbers in the trillions, and the expected number of direct stellar collisions across the full merger event MBE is, for practical purposes, 0, not low, not rare, essentially 0. So the collision is not a collision in any sense the word usually implies. It is a passage, two galaxies flowing through each other, their stars threading the gaps in the opposing structure, emerging on the other side, and then pulled back by mutual gravity, falling through again. The simulations show the two galaxies making multiple passes, approaching, interpenetrating, separating partially, falling back together over a period of hundreds of millions of years before the gravitational binding finally prevents any further separation and the merger locks in permanently. But none of that means the process is peaceful. The absence of stellar collisions does not mean the absence of violence. It means the violence operates at a different scale, not the scale of individual stars, but the scale of the galaxies themselves. The force responsible is tidal gravity, the same fundamental phenomenon that pulls Earth's oceans into bulges on either side of the planet as the moon passes overhead. The difference in gravitational pull between the near side and far side of an object operates on galaxies during a merger, but at a magnitude that makes oceanic tides look like a minor inconvenience. As Andromeda's gravitational field begins to interact with the Milky Way structure, different parts of our galaxy experience different strengths of pull. The near side gets pulled harder than the far side. The result is stretching long tidal streams of stars drawn out from the main body of the galaxy, arcing away into intergalactic space. The familiar spiral arms deformed and eventually dismantled by forces they were never built to resist. The same process happens to Andromeda simultaneously. Both galaxies deform each other. Both galaxies pull streamers of stars from each other's structure. The two objects that entered the encounter as distinct, coherent, elegantly structured spiral galaxies begin to lose their form, their arms stretching, their symmetry breaking, their identities as separate objects gradually dissolving into a single chaotic, gravitationally tangled system, like two enormous jellyfish drifting into each other, their tentacles interweaving, pulling, wrapping, neither one able to maintain its original shape under the forces the other exerts. We do not have to speculate about what this looks like. We can observe it happening in real time, at other galaxies. The antennae galaxies designated NGC 4038 and NGC 4039 are two galaxies currently mid-merger, located approximately 45 million light-years from Earth. The Hubble Space Telescope has imaged them in extraordinary detail, and what the images show are two galactic structures that have already lost their original forms, their material drawn out into long curving streams that extend outward from the merger site like the antennae of some vast insect. The process the Milky Way and Andromeda will undergo in 4 billion years is already visible, already documented, already understood, just happening somewhere else, on a timeline we can observe because their merger started before ours will. As for the Sun and Earth specifically, the simulations by Besla and colleagues and van der Marel and colleagues, published as part of the NASA 2012 analysis, traced the probable fates of stars in the Milky Way's current position. The Sun has approximately a 12% probability of being gravitationally scattered outward during the merger, displaced from its current position in the galactic disk and relocated to a more distant orbit in the new combined structure. Not destroyed, not consumed, simply moved, relocated to the suburbs of a galaxy that will no longer be the Milky Way or Andromeda, but something new, something larger, something without spiral arms, relocated, rehoused, given a new address in a galaxy that did not exist before. Getting relocated sounds manageable, almost gentle, given the scale of everything else involved. But when gravity starts tearing two galaxies apart, something will ignite inside something so beautiful it is blinding, and so destructive it could erase every living thing within thousands of light years. There is a particular kind of permanence that the night sky sells you on if you spend enough time under it. Stand outside long enough away from the cities, away from the noise, in the kind of darkness where your eyes adjust completely and the sky reveals its full depth and the stars stop looking like points of light and start looking like facts. Fixed facts. The kind of facts that predate you by billions of years and will outlast you by billions more. Orion has been Orion for every human civilization that has ever existed. The Pleiades guided sailors 3,000 years ago and still mark the same position tonight. The Milky Way's river of light, that dense, white-hot band overhead, has hung in the same arc above the same planet since before our species existed to name it. The impression is one of absolute structural permanence. The galaxy is not a thing that changes. It is a thing that simply is. That impression is one of the most consequential lies the night sky tells. A galaxy is not a rigid object. It is not a structure built on a foundation, held in place by bolts and beams, resistant to deformation. A galaxy is a gravitational system, a collection of hundreds of billions of objects, each one moving, each one responding to the combined pull of every other object in the system. The whole thing held together not by any solid connection, but by the cumulative gravity of its own contents. It looks stable because the timescales on which it changes are so vast that a human lifetime, or 10,000 human lifetimes, captures nothing but a single frozen instant. The galaxy is changing. It has always been changing. The spiral arms you would see if you could view the Milky Way from outside are not permanent features carved into something solid. They are density waves regions where stars and gas pile up slightly, like cars slowing down at a gradual bend in the highway, then thinning out again as the wave passes. The arms are not even made of the same stars from one galactic rotation to the next. They are patterns, temporary concentrations, beautiful and impermanent. And when Andromeda arrives, this system that looks permanent will discover very quickly that it has no resistance to offer. The force that will do the work is tidal gravity. You already know tidal gravity from a much smaller example. The moon is pulling on the Earth right now, not uniformly, but differentially. The near side of the Earth is slightly closer to the moon than the far side, so the near side gets pulled slightly harder. The result is a stretching effect. The near side bulges toward the moon. The far side bulges away. And in between, the planet is under a continuous squeezing force that manifests on the surface as the rise and fall of ocean tides. The moon does not need to touch the Earth to deform it. Gravity alone, operating across a distance, creates that distortion. Scale this up by the appropriate number of orders of magnitude, and you have what will happen to the Milky Way when Andromeda's gravitational field begins to overlap our own. The near side of the Milky Way will experience a stronger pull from Andromeda than the far side. The difference in force across a galaxy 100,000 light-years wide, when the source of the force is a system massing 1.5 trillion solar masses, is not subtle. It is structural. It is the kind of differential force that does not bend things gently, but stretches them across vast distances, pulling matter away from the main body of the galaxy and drawing it out into long, curving tidal streams that extend into intergalactic space. The spiral arms, those density waves, those beautiful but impermanent patterns, will stop being able to maintain their structure. They will be pulled apart, not explosively, not in an instant. Over hundreds of millions of years, they will be drawn out into streamers of stars and gas, arcing away from the main galactic body, losing their coherence, becoming something that does not resemble a spiral anymore and does not yet resemble whatever the final merged structure will be. The Milky Way you would see from outside, the elegant, symmetric, two-armed spiral that appears in artists' impressions and astronomy textbooks, will stop looking like that. The symmetry will break. The arms will distort. The whole structure will begin to look less like a galaxy and more like something being slowly, inexorably unmade. Here is the thing about that process. We are not guessing about it. We do not have to wait 4 billion years to see whether the models are right. We can look at what is already happening to other galaxies undergoing the same process, at other distances, on timelines that have run ahead of ours. The antennae galaxies, a pair of interacting spirals designated NGC 4038 and NGC 4039, located approximately 45 million light-years away, were already mentioned in the previous section as a comparison for the merger process itself. But for tidal deformation specifically, they are worth examining in more detail, because what the Hubble Space Telescope images show is not just two galaxies colliding. It is two galaxies that have already lost the argument with tidal gravity. Their original spiral structures are gone. In their place are two distorted, chaotic central regions surrounded by long, sweeping arcs of drawn-out material. Tidal tails extending outward for hundreds of thousands of light-years, visible as continuous streams of stars and gas pulled from the main bodies of both galaxies by the same differential gravity that will eventually reshape ours. The name itself, the antennae, comes from these tails. The shape they make is not a spiral. It is not any form the galaxies had before. It is what tidal gravity produces when it has had enough time to work. We are looking at our future in those images, not metaphorically, literally. The same physics, the same forces, the same structural dissolution. The Milky Way and Andromeda will produce something that looks like that, something that does not look like either of them anymore. There is, in this, a specific kind of philosophical confrontation that the universe is staging without asking your permission. The structures we treat as eternal, the constellations, the galaxy overhead, the arrangement of the night sky that has accompanied every human civilization in history, exist on timescales that feel permanent only because we are so short-lived. On the timescale of what is actually happening, the night sky is a snapshot, a single frame from a film that has been running for 13.8 billion years and will continue long after any configuration we recognize has dissolved into something unrecognizable. Nothing about the size of a thing makes it exempt from change. A galaxy is not more permanent than a sand dune because it is larger. It is less visible in its change because the timescale is longer. But the change is happening, has always been happening, will accelerate dramatically when the thing that is coming finally arrives. The universe, it turns out, makes no exceptions for scale. Everything transforms. Everything ends in forms that bear no resemblance to their origins. The spiral arms that look so permanent from below the same arms that have been overhead for every generation of every creature that has ever evolved on this planet are going to be drawn out into something that stretches across hundreds of thousands of light years of intergalactic space, unrecognizable, dissolving. That is not tragedy. It is just physics. But it is also, if you let it land properly, one of the most genuinely humbling facts available to a conscious creature trying to understand where it exists. But tidal stretching is only the first part. When the giant molecular clouds begin to collide, a chain of events will be triggered, something both beautiful and more violent than anything in our galaxy's history. When people try to imagine a collision between two galaxies, they reach for destruction. It is the natural frame. Two enormous things meeting at enormous speed. The mind fills in the expected consequences wreckage, fire, annihilation on a cosmic scale. The previous section addressed why that picture is wrong at the level of individual stars, which mostly pass through each other without contact. But the gas is a different story. Stars are discrete objects. They are widely separated. They pass through without collision. Gas is not discrete. Gas is diffuse. It fills the spaces between stars, spread across the galaxy in vast clouds of molecular hydrogen and helium and dust, occupying the same space the stars move through, extending in enormous formations that dwarf anything solid. The largest of these giant molecular clouds can contain enough mass to form millions of stars. They are spread across the Milky Way and across Andromeda in massive, overlapping distributions. And when the two galaxies begin to interpenetrate each other, the gas clouds do not pass through each other the way the stars do. They collide, not gently, not gradually, at a closing speed measured in tens of kilometers per second. Molecular clouds from Andromeda meet molecular clouds from the Milky Way, and the collision is real, physical, consequential. The gas compresses, pressure increases, and compressed gas, under sufficient pressure, becomes unstable against its own gravity in a way that undisturbed gas is not. In an ordinary molecular cloud sitting quietly in an ordinary galaxy, gravity is constantly trying to pull the gas inward and collapse it into stars. What prevents this, most of the time, is the internal pressure of the gas itself, thermal energy. Turbulence, magnetic fields, which push back against the collapse and keep the cloud in a state of rough equilibrium. The cloud does not collapse because the outward pressure roughly balances the inward gravity. This is why star formation in a normal galaxy is a slow, steady process rather than an instantaneous event. The conditions for collapse are rarely met all at once. Collision changes the conditions all at once. When two molecular clouds ram into each other, the compression is sudden. The pressure increases across a large volume of gas simultaneously. The thermal energy that was providing internal support gets redirected. The turbulent structure of the clouds is disrupted, and across the newly compressed material, the balance tips gravity wins, not in isolated pockets, but across enormous regions simultaneously. The gas does not collapse here and there, slowly, one star-forming region at a time. It collapses everywhere at once, in a cascade, in a burst. This is a starburst, not a metaphor, a technical term in astrophysics for exactly this process, a period of dramatically elevated star formation triggered by a compression event, most commonly a galaxy merger. The rate at which new stars form jumps by factors that make normal galactic star formation look negligible by comparison. 10 times the normal rate, 50 times, in extreme cases, 100 times or more. The galaxy ARP 220 is the reference case. It is a merging system located approximately 250 million light-years away. Two galaxies that have already collided and are in the process of merging. They're gas-driven inward and compressed by the same tidal forces that will operate on the Milky Way and Andromeda. ARP 220 is producing new stars at approximately 100 times the rate of the Milky Way in its dense central region. The star formation is so intense that the infrared luminosity, the heat output from all that stellar birth, is comparable to 1 trillion times the luminosity of the Sun. It is not a galaxy in any ordinary sense of activity. It is a star factory operating at maximum capacity, driven past its normal limits by the violence of the merger that created it. The antennae galaxies, already mid-merger and already showing the tidal deformation described in the previous section, have been imaged by the Hubble Space Telescope in enough detail to count the individual star-forming regions triggered by their collision. The result: thousands of bright young star clusters, each containing tens of thousands to millions of newly formed stars, distributed across the merger zone. The Hubble observations found that approximately a fifth of all the star formation happening in the antennae system is occurring in regions that contain less than 1% of the total area concentrated bursts of creation in the densest, most compressed collision zones. Creation piled into the smallest, most violent spaces. Stars born in a starburst are not born equally. The compression event produces stars across the full range of masses. But the most massive stars, the ones that burn brightest, live shortest, and die most dramatically, are the ones that matter most for what happens next. a star like the Sun will live for approximately 10 billion years, burning steadily, spending most of its existence doing very little of consequence to its surroundings. A star 20 times the mass of the Sun lives for approximately 10 million years. A star 50 times the mass of the Sun burns so intensely that it exhausts its fuel in just a few million years, a cosmic eye blink, a brief, blazing existence that ends in the most energetic event a single star can produce: a supernova. A core collapse supernova, the death of a massive star, releases more energy in a matter of seconds than the Sun will release across its entire 10 billion year lifetime. The shock wave propagates outward through the surrounding gas and dust at thousands of kilometers per second. The light output peaks at a brightness that can outshine the entire galaxy the star lived in, briefly, before fading over weeks and months. And the radiation that accompanies it, gamma rays and X-rays and high-energy particles, extends in all directions through the surrounding space with enough intensity to be genuinely hazardous to any biosphere within a significant radius. In a starburst triggered by a galactic merger, massive stars are being born by the millions. And because massive stars die quickly, they begin dying by the millions before the starburst has even finished producing them. The result is a sustained cascade of supernovae, not one, not a dozen, but an ongoing sequence of stellar deaths distributed across the merger zone, releasing energy and radiation continuously, reshaping the surrounding gas, driving powerful winds that push material outward from the starburst region into the intergalactic medium. This is the violent side of what the Milky Way-Andromeda merger will produce, not the violence of stars colliding that, as established, is essentially non-existent. The violence of stars being born faster than any galaxy in its normal state can sustain, and then dying in the most energetic manner the universe provides, one after another, for millions of years. But here is the part that the destruction frame misses entirely. And it is the part that makes the starburst one of the most genuinely strange phenomena in astrophysics. The same supernova that irradiates its surroundings and drives shockwaves through neighboring gas clouds is also the mechanism by which the universe builds the elements that make chemistry possible. Inside the core of a massive star, nuclear fusion proceeds through a sequence of reactions that produce increasingly heavy elements: carbon, oxygen, neon, silicon, sulfur, all the way up to iron, at which point the energy economics of fusion change and the process stops. Iron cannot be fused into heavier elements through normal stellar burning. The heavier elements, copper, zinc, silver, gold, platinum, iodine, all the elements above iron in the periodic table are produced in the extreme conditions of the supernova itself, in the seconds of the explosion, through rapid neutron capture processes that do not occur anywhere else in nature. Everything heavier than iron that exists anywhere in the observable universe was made in a supernova, or in a neutron star merger, which is a related process. It was not present at the Big Bang. It was not produced by the slow burning of ordinary stars. It was forged in exactly the kind of violent, energetic death that a starburst produces in enormous quantities and then scattered, by the force of the explosion itself, into the surrounding gas and dust, and eventually into the molecular clouds that will form the next generation of stars and their planets. The carbon in every living cell on Earth was made inside a star that died before the Sun formed. The oxygen in every breath was produced by stellar nucleosynthesis and distributed by stellar winds and supernova shockwaves. The iron in your blood was forged in a stellar core and dispersed by a stellar death. The gold in any piece of jewelry anywhere on this planet was produced in a neutron star merger or a supernova and arrived here as part of the solar nebula that collapsed to form the Sun and Earth 4.5 billion years ago. Destruction and creation are not opposites in the universe's operational logic. They are the same process, viewed from different scales. The supernova that sterilizes planets in its immediate neighborhood is simultaneously the mechanism that produces the raw material for future planets, future chemistry, future life. The starburst that lights up a merging galaxy with 100 times its normal luminosity is simultaneously the event that seeds the merger remnant with the heavy elements its future stellar populations will need to build rocky planets around stable stars. The Milky Way Andromeda merger will produce a starburst, almost certainly. Given the gas content of both galaxies, it will produce one of considerable scale, and that starburst will, in the short term, be catastrophic for anything living in the wrong neighborhood at the wrong time. And it will, in the very long term, be exactly the kind of event that makes the next generation of inhabited planets possible. The universe builds by burning. Always has. The atoms in your body passed through this process. The atoms in whatever comes after us will pass through it again. In a merger, we started predicting a century ago and will not live to see. But all of this, the explosion, the destruction, the rebirth, is only the backdrop for the final act. And that final act involves two monsters lying dormant at the center of each galaxy, waiting for the moment to face each other. Everyone has seen the image by now, even if they did not know exactly what they were looking at. In April of 2019, the Event Horizon Telescope collaboration released the first photograph of a black hole ever captured, a glowing orange ring of superheated gas surrounding a darkness so absolute it registered as a hole cut into reality itself. The object was Messier 87 star, the supermassive black hole at the center of a giant elliptical galaxy 65 million light-years away. 3 years later, in 2022, the same collaboration released a second image, this time of Sagittarius A star, the black hole at the center of our own galaxy. Same ring, same darkness, closer, but no less alien. Those images carried a particular cultural weight because they made something real that had existed only as a mathematical abstraction for most of human history. People understood, in an abstract way, that black holes existed. The images made them undeniable. There it was, the thing that warps space-time past the point of return, the thing nothing escapes, photographed, cataloged, measured, sitting at the center of the galaxy we live in. Most people came away from those images with a rough mental model of what a supermassive black hole is: an extraordinarily dense object with gravity so strong that even light cannot escape it past a boundary called the event horizon, sitting at the center of a galaxy, pulling matter inward. That model is correct as far as it goes. What it does not convey is the actual scale of what sits at the center of Andromeda. And that gap between the mental model and the reality is significant. Sagittarius A star, our black hole, the one whose image was released in 2022, has a mass of approximately 4 million times the mass of the Sun. 4 million solar masses is not a number the human brain can actually hold. But consider this for scale: the event horizon of Sagittarius A star, the boundary past which nothing returns, has a diameter of approximately 44 million kilometers. That sounds enormous. It is also smaller than the orbit of Mercury, the most gravitationally extreme object in our galaxy. The thing anchoring hundreds of billions of stars in their orbits fits inside the innermost planet's path around the Sun. Its mass is incomprehensible, but its physical size, relative to the scale of even our solar system, is almost modest. Andromeda's central black hole, designated Messier 31 star, is not modest. Estimates of its mass range from 55 million to 230 million times the mass of the Sun. At the lower bound, it outweighs Sagittarius A star by a factor of more than 13. At the upper bound, it outweighs our black hole by nearly 60. Even accepting the full uncertainty in both measurements, the conclusion is not ambiguous. The object sitting at Andromeda's center is in a categorically different weight class than the one at ours. Not twice as heavy, not 5 times. More than an order of magnitude heavier, possibly approaching 2 orders of magnitude, depending on which measurements you trust and how the uncertainties resolve. 2 objects of this description separated right now by 2,537,000 light-years, one massing 4 million solar masses, the other massing somewhere between 55 and 230 million, are going to spend the next several billion years closing that distance. The process does not happen quickly, and it does not happen in a single step. When the galaxies first begin to interact, the black holes are still at the centers of their respective systems, each one surrounded by its own dense population of stars and gas. As the merger proceeds, as the galaxies pass through each other, as tidal forces disrupt their structures, as the starburst ignites and the combined system begins to take shape, the 2 black holes begin to sink toward the center of the new combined gravitational potential. This is a process called dynamical friction. Stars that pass close to a black hole are accelerated by its gravity, flung outward in a slingshot effect, and in doing so, they carry away momentum from the black hole itself, causing it to slow and sink inward. Over hundreds of millions of years, both black holes drift toward the center of what is becoming Milkomeda, drawn inward by the cumulative effect of millions of individual stellar encounters. Eventually, they find each other. Not suddenly, nothing in this process is sudden. They begin to orbit each other, a binary system of 2 supermassive black holes, circling at distances that are still enormous by human standards, but vanishingly small by galactic standards. Their orbital period at large separations is measured in millions of years. As they radiate energy away through gravitational wave emission and through continued dynamical friction with the surrounding stellar population, the orbit shrinks, the period decreases, the 2 objects spiral inward, slowly at first, then faster as the orbit tightens and the gravitational wave emission intensifies in a feedback loop. Closer means more intense gravitational waves. More intense gravitational waves means faster energy loss. Faster energy loss means the orbit shrinks faster, which means they get closer still. But before that feedback loop can take over and drive the merger to completion, the system encounters a problem, a specific, well-defined, stubbornly unresolved problem that sits at the boundary between what astrophysics can model precisely and what it cannot yet fully explain: the final parsec problem. When 2 supermassive black holes have spiraled down to within approximately 1 parsec of each other. 1 parsec is 3.26 light-years. The mechanism that has been driving their spiral begins to fail. Dynamical friction requires stars to be available for the black holes to gravitationally scatter. But as the binary tightens and scatters stars outward, it depletes the local population of stars on orbits that bring them close enough to interact. The loss cone, the region of orbital parameter space that produces close encounters, empties out. And once it empties, dynamical friction stalls. The 2 black holes sit at roughly 1 parsec separation, close on galactic scales but still impossibly far apart on any human scale. And the mechanism that drove them there is no longer functioning efficiently enough to close the remaining gap. This is the final parsec problem. What happens next? What mechanism, if any, bridges the gap from 1 parsec to the separation at which gravitational wave emission becomes strong enough to drive the merger the rest of the way on its own? The honest answer is that astrophysics does not have a fully satisfying consensus solution. Proposed mechanisms include triaxial galaxy shapes that refill the loss cone through chaotic stellar orbits, the presence of a 3rd black hole that perturbs the binary's orbit, or gas dynamics that provide an additional energy dissipation channel. Each of these works in some simulations under some conditions. None is established as the universal answer. What is observed is that merging galaxies in the real universe do produce merged black holes. We see the results. We detect the gravitational waves. We observe post-merger systems with single central black holes that could only have formed by merging two smaller ones. So the problem is solved by the universe, even if it is not fully solved by our equations. Nature finds a way. It does not always show us how. There is something almost human about this situation. Two objects that have been approaching each other for billions of years, that have overcome the vast separation of intergalactic space, that have survived the chaos of a full galactic merger, and then find themselves stuck at the last step. The final distance is the hardest. The physics that carried them across millions of light years is not sufficient to cover the final three. It is the kind of irony the universe seems to specialize in, unintentionally and without any regard for how it reads from the outside. The resolution, when it comes, is final, absolute. The two black holes cross the threshold where gravitational wave emission dominates everything else. The orbit decays rapidly. And in the last fraction of a second before contact, the system releases more energy than has been released by any event in the history of the galaxy that contains it. And when the two black holes finally meet, what happens next will send a shockwave through the very structure of space and time, spreading across the universe. This is the most violent event in the history of Milkomeda, and we already know exactly what it looks like. In September of 2015, at 4:51 in the morning Eastern Time, two detectors, one in Louisiana, one in Washington State, registered a signal. The detectors were part of LIGO, the Laser Interferometer Gravitational Wave Observatory, and what they registered was a distortion in the length of their 4-kilometer detector arms so small that describing it requires a comparison that borders on absurdity. The displacement was approximately 1,000th the diameter of a proton, not a millimeter, not a nanometer. 1,000th of a proton diameter, detected across 4 kilometers of laser interferometry by instruments sensitive enough to register a change in length smaller than any physical object that has ever been directly measured. The signal lasted less than a second. When the frequency data was converted to audio, when the chirp of two black holes spiraling together and merging was played through speakers, it sounded, to human ears, like a brief, rising tone. A thump, almost nothing. That almost nothing was the gravitational wave signature of two stellar mass black holes merging approximately 1.3 billion light-years away. The energy released in the final fraction of a second of that merger was equivalent to approximately 3 times the mass of the Sun, converted entirely to energy more than the energy output of all the stars in the observable universe combined. For that brief instant, released as a ripple in the geometry of space-time that spread outward at the speed of light and arrived at Earth 1.3 billion years later as a displacement of 1,000th of a proton. That was two stellar mass black holes, objects of roughly 30 and 35 solar masses each. The black holes that will merge at the center of Milkomeda are supermassive, millions to hundreds of millions of solar masses each. The gravitational wave signal from their merger will not be a brief chirp. It will be a sustained, low-frequency roar. Not at the high frequencies LIGO detects, but at frequencies so low they correspond to periods of years to decades, far below anything a ground-based interferometer can measure. To detect gravitational waves from supermassive black hole mergers requires an entirely different approach. The approach is called a pulsar timing array. It uses the universe's own infrastructure, specifically millisecond pulsars, which are neutron stars spinning so rapidly and so consistently that they emit radio pulses with a regularity that rivals atomic clocks. A millisecond pulsar spinning 300 times per second produces a radio pulse every 3 milliseconds. And the timing of those pulses is stable to within nanoseconds over years of observation. If a gravitational wave passes between Earth and a pulsar, it stretches and compresses the space-time between them by a tiny amount enough to shift the arrival time of the pulses by nanoseconds in a correlated pattern across many pulsars distributed across the sky. By monitoring a network of millisecond pulsars simultaneously and looking for those correlated timing deviations, the characteristic fingerprint of a gravitational wave background astronomers can effectively use the galaxy itself as a gravitational wave detector. Not a 4-kilometer detector arm, but a detector with baselines measured in thousands of light years. In 2023, this approach produced its first major result. NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, along with the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array, simultaneously published analyses finding strong evidence for a gravitational wave background, a low-frequency signal permeating the data from their pulsar networks. Consistent with the predicted signature of gravitational waves produced by a cosmological population of supermassive black hole binaries throughout the universe. Not one merger, not a handful. The blended signal from an enormous number of supermassive black hole pairs spiraling together across cosmic history. Their gravitational waves overlapping into a background hum that the pulsars register as a correlated noise floor in their timing data. The universe has been making this sound for billions of years. In 2023, we finally heard it. What the Milky Way Andromeda merger will eventually contribute to that background billions of years from now. When the two central black holes finally close their last parsec and merge will be a signal of extraordinary power. A single event from a binary system massing hundreds of millions to over 1 billion solar masses combined, releasing energy and gravitational waves at a level that will propagate outward through the local group and beyond. Detectable in principle by any civilization anywhere in the observable universe with a sufficiently sensitive instrument. The merger of Sagittarius A star and Messier 31 star will be, by most measures, the most energetic gravitational wave event in the history of the local group, and the resulting object, a single supermassive black hole of combined mass. Perhaps 300 million solar masses or more will sit at the center of whatever Milkomeda has become by then, anchoring the remnant of two galaxies that spent billions of years becoming one. That remnant will not look like either of its parents. The Milky Way is a spiral galaxy. Andromeda is a spiral galaxy. Their merger will produce neither. When two spiral galaxies of comparable mass collide and merge, the outcome is an elliptical galaxy, a smooth, featureless, roughly spheroidal distribution of stars with no disk, no spiral arms, no coherent rotational structure. The elegant geometry of a spiral, the disk, the arms, the central bulge. The whole rotating machinery requires a specific set of conditions to maintain. It requires that the stars in the disk mostly orbit in the same direction, in roughly circular orbits, in a relatively undisturbed gravitational environment. A major merger destroys all of that. The tidal forces scramble the orbital directions. Stars that were moving in coordinated circular paths get deflected into elongated, tilted, chaotic orbits that distribute them throughout a three-dimensional volume rather than keeping them in a thin disk. After the merger is complete and the system has had time to relax into a new equilibrium, what remains is a smooth, slowly rotating ellipse of stars in no structure, no arms, no disk, just a cloud of stars bound together by gravity, settling into the simplest configuration gravity allows. Astronomers have given this future object a name, informal, but widely used in the literature, Milkomeda, the merger product of the Milky Way and Andromeda, a giant elliptical galaxy that will contain more than 1 trillion stars, anchored by a supermassive black hole of combined mass, drifting through a local group that will itself be increasingly isolated from the rest of the universe as cosmic expansion carries other galaxy clusters beyond the horizon of gravitational influence. The fate of the Sun and Earth in this picture is clarifying in its finality. By the time the galactic merger is complete, approximately 6 billion years from now, the Sun will have already exhausted its core hydrogen supply. It will have expanded into a red giant, swelling to a radius somewhere between the current orbits of Earth and Mars, depending on which stellar evolution models you consult. Earth's oceans will have boiled away billions of years before that. The surface will be sterilized. Whatever life existed on this planet will have had to leave or die long before Andromeda makes its first close pass. The Milkomeda merger, for any biological perspective centered on Earth, is irrelevant, not because it is too distant to matter, but because nothing that matters biologically will still be here to be affected by it. The universe's schedule, it turns out, does not consult ours. An elliptical galaxy is, in astronomical terms, old. Not old in the sense of having existed for a long time, though, that too, but old in the sense of being past its productive period. Elliptical galaxies contain very little cold gas. Cold gas is the raw material for star formation. Without cold gas, new stars do not form. Milkomeda, after the merger and the starburst that preceded it, have consumed or expelled most of the available gas, will settle into a phase of quiescence, a galaxy that is slowly, over billions of years, using up its existing stars without making new ones. The brilliant blue clusters of young massive stars that currently make spiral galaxies glow will be gone. What remains will be the longer-lived, redder, lower-mass stars, orange and yellow dwarfs. Red dwarfs burning slowly in a galaxy that is, by every measure, running down. Beautiful in a muted way. Ancient in a way the Milky Way is not. A structure in its final configuration, having exhausted the energetic youth that spiral galaxies represent. There is something almost elegiac about that picture. Two spiral galaxies, each one a vast, ongoing engine of star formation. Each one surrounded by satellites. Each one carrying its own history of past mergers written into its structure, spending billions of years approaching each other, colliding, passing through each other, being deformed and stretched and disrupted, eventually locking together into a single object that is quieter and slower and older than either of them was alone. The spiral arms, which will have been dissolving for hundreds of millions of years before the merger is complete, will leave no trace in the final elliptical. The structure of the Milky Way that you would see if you could view it from outside, the thing that makes it visually distinct, that gives it its particular shape in the sky of any neighboring galaxy will be gone, incorporated, dissolved into something new. We know all of this: the orbits, the timeline, the energy, the final shape with remarkable precision. But there is one thing we will never be able to do: set foot on Andromeda to see it with our own eyes. And the reason is not a lack of technology. It is that the universe has laid down an absolute rule that no civilization can ever break. There is a particular arc to human history that makes a certain kind of optimism feel almost mandatory. Columbus stood at the edge of the known world in 1492 and sailed into it anyway. 3 weeks of open ocean, no landmarks, no guarantee of anything on the other side, and he kept going. 3 centuries later, the Wright brothers flew 120 feet at Kitty Hawk, 12 seconds of powered flight, barely enough to cross a tennis court, and 66 years after that, human beings were standing on the moon. The gap between 12 seconds of flight and a lunar landing is 66 years. The gap between Columbus and the International Space Station is 500 years. Every time the species reached what looked like an absolute limit, it turned out to be a temporary one, a problem of engineering, not of physics. A question of when, not of whether. So the question about Andromeda feels, at first, like the same kind of question. We cannot get there now. We cannot get there with anything we have built. But we said that about the moon in 1903, and we said that about Mars in 1960. And both of those statements turned out to be wrong within a generation. Why should Andromeda be different? The answer is that Andromeda is not a problem of engineering. It is a problem of physics. And those are not the same thing. Start with the number. Andromeda sits 2,537,000 light-years from Earth. 1 light-year is the distance light travels in a year. Moving at approximately 670 million miles per hour, the fastest speed that physics, as currently understood, permits for anything carrying information or mass. 2,537,000 of those distances, laid end to end, is the gap between us and our nearest large galactic neighbor. Now consider Voyager 1, launched in 1977. It is the farthest human-made object from Earth that has ever existed. It crossed into interstellar space in 2012, becoming the first artifact of human civilization to leave the heliosphere, the bubble of solar wind that defines the outer boundary of our sun's direct influence. As of now, it is traveling at approximately 38,000 miles per hour. That is fast by any standard a human body can actually register. It is faster than any commercial aircraft by a factor of roughly 50. It is fast enough to cross the continental United States in about 5 minutes. At that speed, Voyager 1 needs approximately 40,000 years to reach Proxima Centauri, the closest star to the Sun, at 4.24 light-years. 40,000 years. The entirety of recorded human history fits inside 12,000 years. Agriculture is 10,000 years old. Writing is 5,000 years old. 40,000 years from now, at Voyager 1's current speed, we would be arriving at the first star. To reach Andromeda at that speed requires approximately 600 billion years. The universe is 13.8 billion years old. 600 billion years is roughly 43 times the current age of the universe. It is a duration so far beyond any human or biological or geological or even cosmological reference point that the word years stops having any real content. The number is not large. It is a different category of quantity than anything the word large is built to handle. Fine. Go faster. This is the obvious response, and it is the right one to examine carefully because it leads directly to the wall. Special relativity. Einstein's theory, published in 1905 and confirmed by every experiment conducted in the century since, contains a specific and unambiguous statement about what happens to matter as it accelerates toward the speed of light. The relativistic mass of an object increases as its velocity increases, not linearly. The relationship is governed by the Lorentz factor, which grows slowly at first, then faster, then catastrophically as the velocity approaches the speed of light. At 90% of light speed, the effective mass of an object is approximately 2.3 times its rest mass. At 99%, it is about 7 times. At 99.9%, it is about 22 times. At 99.99%, about 70 times. The curve does not level off. It continues upward without limit. What this means in practical terms is that accelerating a mass to higher and higher fractions of light speed requires proportionally greater and greater energy, not just more energy, but more energy in a ratio that increases without bound as you approach the limit. To accelerate any object with mass to exactly the speed of light requires infinite energy, not a very large amount of energy, not more energy than we currently know how to generate. Infinite, a quantity that has no physical meaning as a finite resource because it is not finite. Think of it this way. You are pushing a shopping cart empty. It moves easily. You add weight, it gets harder. You keep adding weight, doubling it, tripling it, and each addition makes the next push harder than the last. Now imagine the weight keeps increasing, not just as you add items, but as the cart gets faster, as if the act of moving the cart caused it to become heavier. And the heavier it became, the harder it was to push faster, and the harder you pushed, the heavier it became. There is no point at which you overpower this feedback. There is no engine you can install. The physics of the situation guarantees that the cart never reaches the limit you are pushing toward, no matter how much force you apply, because the limit is defined precisely as the point at which the required force becomes infinite. That is what special relativity says about matter moving at the speed of light. Not that we lack the engineering, that the physics prohibits it, categorically, for any object with mass, and light itself. Traveling at its own speed across 2,537,000 light-years would need 2,537,000 years to make the crossing. Even granting the impossible, a spacecraft that somehow traveled at the speed of light, the journey takes 2.5 million years. That is longer than the entire existence of the genus Homo. It is longer than modern humans have existed as a species by a factor of more than 12. Humanity crossed the Atlantic in weeks, reached the moon in days, sent probes to the edge of the solar system in decades. Each of those achievements required pushing against limits that turned out to be technological rather than physical. The limit on interstellar and intergalactic travel is not technological. It is written into the structure of space-time itself by the same equations that make GPS satellites work and nuclear reactors function, and particle accelerators produce the results they produce. The speed of light is not a barrier we have not yet broken. It is a feature of the universe, not a bug in our engineering. The universe, which has given humanity fire and agriculture and flight and nuclear energy and the internet, draws a very clean line at the edge of the local group. On one side of the line, achievable, on the other, not, for any object made of the matter we and everything we have ever built are made of. It crossed the Atlantic, it reached the moon, it sent probes past the solar system's edge, and then the universe quietly raised its hand and placed a sign at the boundary of interstellar space that reads, "In the language of physics, this is where the rules change. This is the part that does not bend." But scientists and engineers do not give up easily. There are bold ideas, generation ships, laser sails, space warps. Can any of them work? The answer will make you admire human creativity and feel genuinely imprisoned at the same time. The ideas exist. They are serious ideas, developed by serious people, published in peer-reviewed journals, debated at conferences, funded at various levels by agencies and private organizations that do not spend money on things they consider completely frivolous. The fact that they exist at all is a testament to the particular stubbornness of human imagination when confronted with a problem it cannot immediately solve. The imagination keeps working even when the physics is not cooperating. That stubbornness deserves genuine respect. But respect for the creativity does not change what the numbers say. And the numbers, in every case, say the same thing. The first idea is the generation ship. The concept has been part of science fiction since the early 20th century and has been taken seriously by aerospace engineers and futurists since at least the 1960s. The premise is straightforward if no single human lifetime is long enough to make an interstellar journey. Build a ship large enough to contain a self-sustaining community and send multiple generations. The people who launch the ship will not be the people who arrive. Their grandchildren, or their grandchildren's grandchildren, will be the ones who step off at the destination. The ship is not just a vehicle. It is a world. It contains agriculture, medicine, social structure, reproduction, death, culture, everything a civilization needs to persist across the duration of the journey. For nearby stars, Alpha Centauri, Proxima Centauri. Tau Ceti generation ships represent a genuinely imaginable future technology, if not a near-term one. The journey times, at speeds achievable with sufficiently advanced propulsion, run to centuries or a few millennia. Long, but not biologically impossible, not structurally inconceivable. For Andromeda, the mathematics collapses immediately. At any speed, a generation ship could realistically achieve, which means, given the energy constraints of the previous section, speeds well below the speed of light. The journey time to Andromeda is measured in billions of years. Not millions, billions. The Earth is 4.5 billion years old. The journey a generation ship would need to make to reach Andromeda, at any propulsion system currently conceivable without violating known physics, spans a duration comparable to the entire age of the planet it departed from. No biological lineage persists across that duration, no social structure, no cultural continuity, no institutional memory survives billions of years of transmission through finite human generations in a closed environment. The generation ship concept reaches its limit not at some engineering threshold, but at a simple biological one. Living things change over billions of years, and what emerges from a ship after that duration would bear no meaningful relationship, genetic, cultural, linguistic, or psychological to the civilization that launched it. The second idea is more technically grounded and is actually being developed for a much shorter mission. Breakthrough Starshot is a research initiative founded in 2016 with the explicit goal of sending a small probe to Alpha Centauri within a generation. The concept involves a gram-scale spacecraft, essentially a microchip with a sail pushed by an array of high-powered ground-based lasers to approximately 20% of the speed of light. At that speed, the journey to Alpha Centauri takes about 20 years. The probe cannot decelerate on arrival. It would fly through the system in hours, but it could transmit data back during that window. It is an extraordinary idea, genuinely achievable in principle with technology that is not wildly beyond current capabilities. Apply it to Andromeda. 20% of light speed covers 2,537,000 light-years in approximately 12,500,000 years, 12.5 million years, minimum, to reach the destination. And the probe arrives with no ability to stop. It passes through the outskirts of Andromeda in a matter of days and continues into intergalactic space beyond. If it had functional transmitters, which after 12 million years of interstellar radiation exposure, it almost certainly would not, the signal it sent back would take another 2.5 million light-years to return. Total elapsed time from launch to receiving the first transmission from Andromeda's vicinity, approximately 15 million years. Longer than our entire genus has existed. Longer than our species will likely exist, given historical extinction rates for comparable organisms. There is no civilization on Earth that could launch this mission, wait 15 million years, and still be there to receive the results. The third idea is the most radical and the most discussed in theoretical physics circles, warp drive. The specific proposal that gets taken seriously, not as science fiction, but as a legitimate solution to Einstein's field equations, is the Alcubierre metric, published in 1994 by Mexican physicist Miguel Alcubierre. The idea is elegant in its structure. Special relativity prohibits matter from moving through space faster than light, but it does not prohibit space itself from moving. The universe does exactly this during cosmic inflation and continues to do it in the form of the expansion that Hubble measured. Alcubierre proposed a geometry of space-time, a mathematical solution to Einstein's equations in which a bubble of flat space-time is created around a spacecraft. The space ahead of the bubble contracts. The space behind it expands. The spacecraft inside the bubble does not move through space at all. In the relativistic sense, it sits still while space carries it. There is no violation of the speed limit because the limit applies to motion through space, not motion of space. The problem is not the mathematics. The mathematics works, in the sense that the metric Alcubierre wrote down is a valid solution to the field equations. The problem is what the metric requires in order to exist physically. To maintain the bubble geometry, you need a region of negative energy density, what physicists call exotic matter, in a configuration that wraps around the spacecraft. The energy requirements in the original 1994 formulation were staggering, on the order of the mass energy of Jupiter, converted entirely to exotic matter. Subsequent refinements by Harold White and others at NASA have proposed modified geometries that reduce this requirement substantially. But even the most optimistic current estimates still require exotic matter in quantities that have never been produced, in configurations that have never been achieved, using physics that has been theoretically proposed but not experimentally confirmed to exist in the necessary form. Exotic matter with negative energy density is not entirely hypothetical. Small amounts have been observed in phenomena like the Casimir effect. But between tabletop Casimir observations and the Jupiter mass negative energy densities needed for an Alcubierre bubble sits a gulf of technology, energy, and physics that is, at present, completely unbridged. And even if all of that were solved, the exotic matter produced, the bubble created, the spacecraft enclosed theoretical analyses by physicists, including Stephen Hawking and Kip Thorne, have raised fundamental questions about the stability of the geometry and its compatibility with quantum field theory. The bubble may be inherently unstable. The radiation effects at its boundary may be catastrophic. The causal structure it creates may produce paradoxes that the universe's own physics would prevent from forming. The warp drive is not ruled out the way an Alcubierre drive running at 101% light speed is ruled out. It is ruled out in a more complicated way, a way that involves the uncertainty of physics at the boundary between general relativity and quantum mechanics. And that uncertainty cuts both ways. It might be possible, but there is currently no reason to believe it is. The pattern across all three ideas is the same. Each one represents genuine ingenuity. Each one works in some domain. The generation ship works for nearby stars over centuries. The laser sail works for tiny probes going to the nearest neighbors. The warp drive works mathematically. But each one, when applied to the specific problem of reaching Andromeda, runs into a wall that is not an engineering wall, and not a funding wall, and not a political will wall. It is a physics wall, a constraint imposed by the structure of the universe itself, at the level where the equations live, before any engineer ever picks up a tool. This is not the same as saying it is impossible forever. Physics has surprised us before. There may be things about the structure of space-time that we do not yet know. There may be a discovery, not yet made, that changes the category of the problem. The way the discovery of electromagnetism changed the category of communication in the 19th century. We cannot rule that out, but we also cannot assume it. What we can say, with the physics we have and the experiments we have run and the universe we have observed, is this for matter made of the ordinary stuff? This planet and everything on it is made of, obeying the laws of physics as currently understood. Traveling to Andromeda is not a problem we do not yet know how to solve. It is a problem the universe may not permit to be solved, at least not in any form that the word travel was built to describe. We live in a fishbowl. The fishbowl is the Milky Way. We can see the fishbowl next to ours Andromeda in extraordinary detail, 2.5 million light-years away. We can count its stars and measure its mass and photograph its core and predict its future with precision. But the glass of the universe, the speed of light, the behavior of mass under acceleration, the energy requirements of every alternative we have imagined stands between us and it with a completeness that no engineering project has yet found a way around. But here is the strangest thing of all, despite being completely imprisoned. We are the only creatures in history who know exactly that we are imprisoned and why. And that capacity for understanding may be the greatest thing in this universe. There is a default way human beings measure importance. It runs on size. The mountain is more impressive than the hill. The empire that stretched across continents is remembered longer than the kingdom that fit inside a valley. We have been doing this forever, ranking significance by scale, assigning gravity to whatever occupies the most space. In most contexts, that shaped our evolution. It was not an irrational instinct. Larger things genuinely were more consequential. Apply that instinct to the universe, and the conclusion is immediate and brutal. We are on a planet 8,000 miles wide, orbiting a star of no particular distinction, positioned 2/3 of the way out from the center of a galaxy containing up to 400 billion other stars, in a universe holding at least 2 trillion galaxies. By the size metric, we are not even rounding error. We are the kind of thing that gets lost in the error bars of an astronomical measurement. But here is where the metric breaks down completely. Andromeda, 1 trillion stars. A central black hole massing up to 230 million solar masses. 1.5 trillion times. The mass of the sun does not know it exists. It does not know it is moving toward us. It does not know that a civilization 2.5 million light years away has measured its mass, mapped its double nucleus, calculated its trajectory, and named the galaxy that will result from their eventual merger. Andromeda cannot know any of this. It is vast and complex and gravitationally magnificent, and it has no inner life whatsoever. Now consider what fits inside a human skull. Roughly 1.4 liters of tissue, running on about 20 watts of power, built from carbon and oxygen and iron that supernova explosions scattered through the galaxy billions of years ago. Inside that small organ, something happened that has no confirmed parallel anywhere in the observable universe. The universe became aware of itself. Those brains in their collective, generational enterprise called science calculated the orbital mechanics of 2 galaxies massing a combined 2.5 trillion solar masses. They predicted the timing of a collision 4 billion years away. They detected gravitational waves from merging black holes a billion light years distant. They photographed the event horizon of a black hole 65 million light years away. All of that, accomplished by creatures who 100,000 years ago were hunting with sharpened stones. In 1924, we did not know Andromeda existed as a separate galaxy. 1 century later, we know the mass of its central black hole, the probability distribution for where the sun will end up after the merger, and the gravitational wave signature the eventual black hole collision will produce. The rate of learning compressed into that century has no precedent in the history of the species, and no confirmed parallel anywhere else we have looked. In 1990, Voyager 1 turned its camera back toward the inner solar system from 4 billion miles away. Earth appeared as a pale blue dot, less than a pixel across, suspended in a beam of scattered sunlight. Carl Sagan wrote that on that dot. Every human being who ever lived had spent their entire life, every war ever fought, every civilization ever built, every act of love and cruelty and hope, all of it, on something too small to show up clearly in a photograph. But the dot looked back. It sent a spacecraft 4 billion miles away, turned its camera around, and understood what it was seeing. Andromeda cannot do that. The Virgo supercluster cannot do that. The observable universe, in all its 2 trillion galaxies, cannot do that except through us. And whatever other minds may exist elsewhere that we have not yet found. We are, as far as any evidence suggests, the only things in the local group that know the local group exists. That is not smallness. That is the strangest and most improbable thing the universe has produced in 13.8 billion years. We are the only species in the known universe to have scheduled our own galaxy's apocalypse and calm enough to discuss it on YouTube. But that capacity for understanding leads to a deeper question, one that physics cannot answer. If we are the only conscious beings in the galaxy, what does that understanding mean? And if we are not, if somewhere among Andromeda's 1 trillion stars, other minds are looking back at us, then what happens to them when the two galaxies finally meet? There is a version of this story that ends in smallness. The universe is vast. We are negligible. We cannot reach our nearest neighbor. And the atoms that make up every human being will eventually be distributed through an elliptical galaxy that retains no memory of the spiral arms it came from. That version is factually accurate, but there is another version, also factually accurate. Right now, expanding outward from Earth in every direction at the speed of light, there is a sphere of electromagnetic signals approximately 240 light-years across and growing. Every radio broadcast ever made, every television signal ever sent, all of it moving through the galaxy at the maximum speed the universe permits, carrying evidence that something on a small planet learned to encode information and send it into the dark. That sphere will reach the edge of the Milky Way in approximately 100,000 years. It will reach the vicinity of Andromeda in 2.5 million. The signals will be faint, beyond any instrument we currently possess to detect, but the physics governing their travel contains no clause that says they stop. They do not stop. Viktor Frankl survived the Nazi concentration camps and emerged to write one of the most carefully reasoned arguments ever made about meaning under constraint. His central claim, meaning does not derive from power or scale or freedom of movement. It derives from the capacity to choose one's orientation toward one's circumstances. A person in a cell retains the last human freedom, the freedom to determine what the imprisonment means. The cell does not decide. The mind inside it does. The universe has placed us in a cell, a large and beautiful cell, a galaxy of hundreds of billions of stars, with room enough for everything biological life has ever accomplished, but a cell. The glass walls are the speed of light and the thermodynamics of acceleration. We can see through those walls with extraordinary clarity. We cannot pass through them. But the mind inside has done something cells are not supposed to enable. It has understood the cell, measured the walls, identified their composition, deduced the reasons for their existence, and written all of that down in a form that travels at the maximum speed the universe allows. Consider the full arc. In 1924, we did not know Andromeda existed. In 2012, NASA modeled the full merger sequence with enough precision to specify the timing of the first close encounter. In 2023, pulsar timing array networks detected the gravitational wave background that includes precursors to the kind of merger our two central black holes will eventually produce. Each of those steps made us no smaller. They made the understanding larger. Andromeda is coming. It has been coming for longer than our species has existed. The spiral arms of the Milky Way, overhead for every conscious creature that has ever evolved on this planet, will dissolve into a quiet elliptical over hundreds of millions of years, leaving no trace of the structure they once formed. And in the brief window of cosmic time between Hubble's night at the Hooker telescope and whatever endpoint awaits us, something happened on a pale blue dot that may be among the most remarkable things the universe has yet managed. A collection of matter became curious about the rest of the matter, built instruments to examine it, and found it beautiful. Andromeda will become us. We will become Andromeda. The atoms are not precious about their arrangements, but the understanding, the act of knowing. The moment a mind looks at 2 trillion galaxies and grasps what it is seeing, that is something the universe spent 13.8 billion years producing. And it happened here. But this is only one of the countless stories the universe is telling, and most of those stories are still drowning in darkness. We began with a field at night and the feeling of being at the center. It turns out to be wrong in almost every factual detail, and right in the one way that matters most. We are not at the center of the Milky Way. We are not in a privileged position in the local group. The Milky Way is one of 2 trillion galaxies, unremarkable by every measurable parameter. And yet here we are, having calculated all of that, having measured our own insignificance with instruments we built from sand and metal and mathematics, and looked at the result without looking away. Everything science has revealed about Andromeda, about Milkomeda, about gravitational waves and starburst events and the final parsec problem is only the surface. We have barely touched the edge of the abyss. There are 2 trillion other galaxies, most unobserved. Dark matter makes up 27% of the universe's total mass energy, and we do not know what it is. Dark energy makes up 68%, and we understand it even less. Together, they are 95% of everything the universe contains. Everything we have ever seen or touched or measured is the remaining 5%. The darkness is not empty. It is full of things we have not yet learned to see, and that is not a reason for despair. Perhaps the greatest thing about being human is not that we can go to Andromeda. We cannot. It is this, that we can sit here on this dust grain and know that it exists, that it is beautiful, that one day it will become us and we will become it, and that somehow is enough.